Hello and welcome to this clip on Born-Haber cycles and lattice enthalpies. We'll start by looking at lattice enthalpy as a way of quantifying the strength of ionic bonding in an ionic lattice, and look at how we illustrate the stages in the dissociation or formation of ionic lattices using Born-Haber cycles based on the principles of Hess's law. We'll then go on to review some of the key processes involved, in what order they have to happen, and how we can use key data to calculate the enthalpy changes involved in the process. Then we'll go on to look at the application of this lattice enthalpy idea to ionic compounds in solution, and the relationship and connection between lattice enthalpy and enthalpy of hydration during the process of dissolving an ionic solid. It's assumed that you're familiar with ionic lattices and also the use of Hess's law from the first year of your A-level chemistry course. If you're unsure at all about either of those ideas, it might be worth going back and having a look over your notes before you go any further. So just to recap, all chemical processes have an activation energy and also an enthalpy value, usually written as delta H. Obviously the enthalpy change of a process can be exothermic or endothermic. When we draw out such changes in diagram form, such as this enthalpy profile diagram, endothermic processes are given an upward arrow to show that energy is being taken in, and delta H is positive. And it's the opposite for exothermic processes. They're given downward arrow to show that energy is being given out, and delta H is negative. This is just a little review of how we draw out arrows in exothermic or endothermic changes, so you can see when we look at Born-Haber cycles a little bit later on in the clip whether the processes individually are endothermic or exothermic. So just to illustrate what we've spoken about a moment ago, this is an example of an exothermic process. You can see quite clearly that delta H is negative and it points downwards. Okay, so let's look at some of the processes that are involved in lattice enthalpy. So as you probably recall from your first year, an ionic lattice is held together by strong electrostatic attractions between oppositely charged ions. But we need to think about what has to happen for this ionic lattice to dissociate, and also in what order do the processes have to occur. So we start with the ionic solid lattice. You'll notice I've drawn a solid line. That solid line represents the energy level at which the solid ionic lattice exists. The next line is higher up. This is because the elements are in their standard states, and when an ionic solid lattice is formed from elements in their standard states, in other words, the standard enthalpy of formation, it's an exothermic process. So, getting from the elements in their standard states to an ionic solid lattice is the equivalent of delta FH. Now if you're not sure what delta FH is, you need to go back and look this up. The next process that has to happen once you have the elements in their standard states is you have to then turn all the elements into gaseous atoms. This is a process called atomization. Once you've got the gaseous atoms, you then have to turn them into gaseous ions. So to get from the gaseous ions of the elements back to the ionic solid lattice is the lattice enthalpy, and it's an exothermic process. So the diagram above is a basic outline we use for a Born-Haber cycle. So before we go any further, let's have a look at what some of these processes actually mean. So I've laid out all the different terms with their definitions. I've put a picture from the last screen of the NaCl lattice, so I'll take each one in turn and show you how to draw it out as an equation. It might make it a little bit easier to understand what's going on. So this first equation represents the standard enthalpy of formation or the process that takes place for which the standard enthalpy of formation is the enthalpy change. You've got 1 mole of your compound, NaCl, you've got it being formed from its elements, and all the reactants and products are in their standard states. Notice that it's half Cl2. That's because to make 1 mole of NaCl, if you had 1 mole of Cl2, you'd have too much chlorine. So it has to be a 1-to-1 ratio of the atoms to make the ions in the ionic lattice. So as I do these, you might want to jot down the equation next to the definition, applying it to NaCl, a common lattice that everyone's heard of. So it'll make it make sense for you. So in each of these cases, the element is in its standard state to start with, and it's turned into 1 mole of gaseous atoms. Now, it might seem strange to look at sodium as a gas. Try and move away from whether that appears normal to you or not. It's simply describing this particular process called atomization. So we're looking at each individual process in turn, no matter how strange it might seem, no matter how much it might go against your instincts, what you're used to, what you've come across before. This particular process is the creation of 1 mole of gaseous atoms from an element in its standard state under standard conditions. And whatever enthalpy change accompanies that is called the standard enthalpy of atomization. So next up is the first ionization energy. This only happens to things when an electron is removed. It doesn't mean that it's automatically turned into an ion, it's turned into a 1+ ion. It's very important that it's always a 1+ ion. If it was a 2+ ion that was being formed from a 1+ ion, obviously that would be the second ionization energy. So in this case we're just interested in the first ionization energy, and in the NaCl lattice that applies to sodium. So looking at the chlorine this time, the chlorine atoms are in gaseous form, or they've been atomized, so then what has to happen is they gain an electron, 1 electron for each individual chlorine atom in gaseous form, and that forms gaseous chloride ions. So here we're dealing with the lattice enthalpy of sodium chloride. Notice that the sodium and the chlorine are actually in sodium plus and chloride form. They're in the ionic form and they're gaseous. And this is why we spoke earlier about things having to happen in a certain order in a Born-Haber process. For Na plus and Cl minus to be produced in this format, 1 mole of each, in gaseous form, all the other processes have to happen in the correct order for these gaseous ions to be formed. So let's look at another group 1 chloride, cesium chloride. Cesium is in the same group as sodium. So we've got all of the different processes lined up in the correct order. So the problem is that it's very difficult to measure the direct route. To measure lattice enthalpy directly is impossible, essentially. So what you've got to do is apply Hess's law. So because we've got all this data for each stage of that indirect route, then we can actually use the indirect route to calculate the lattice enthalpy. So let's have a think carefully, just for a moment, about how I'm going to work out the lattice enthalpy. If you look at where I've labelled the start and finish points in the Born-Haber cycle, I can't work out, or measure, the direct route. We've established that already. So by doing the indirect route, what I'm doing is I'm adding all the enthalpy values as I go, but look at the second point in the bottom left hand corner. If the route takes me against the arrow of the enthalpy change, like I've now annotated, what you have to do is reverse the sign. So I'm going to now put these numbers in for you. That gives me minus 663 kilojoules per mole to the minus 1. So that's one way of doing it. There is another route which shows you how to use Hess's law, and I'm going to take you through that one now. So using Hess's law involves comparing two routes for creating your lattice. You've got route 1, which involves going through each individual process we've talked about, including the lattice enthalpy, and we've got route 2, which involves simply making the lattice and the elements in their standard states. Now the important thing to remember is that route 1 equals route 2 in terms of total enthalpy change. So therefore this applies Hess's law up in the top right hand corner. We're assuming that we're using standard enthalpy changes in each case, so therefore the initial and final conditions are the same according to the quotation of Hess's law in the top right hand corner box. So that gives us this particular expression. Now what we've got to do is rearrange to make the lattice enthalpy the subject, which also gives us minus 663 kilojoules per mole to the minus 1. So the two different techniques end up with the same answer. What you might be asked to do is to use Hess's law to calculate lattice enthalpy. If they ask you to do this, the second technique we've just done is the one to use. If they don't specifically ask you to apply Hess's law in the question, you can probably use either of the two techniques and you'll be fine, because you can see mathematically that they actually end up with the same value. So on a personal level, I would suggest the second method, as it seems to be the one that's outlined in most textbooks, so therefore it's probably favoured by most examiners. It's probably a slightly better method because it actually demonstrates to the examiner that you understand how Hess's law is being used. The first method is just a sort of mathematical coincidence, it's slightly oversimplified. The second method shows the person checking your exam that you understand the link between Born-Haber cycles and Hess's law, which is an important concept, an important connection to make, and obviously then an important connection to demonstrate to your examiner that you've made. So let's have a quick look before we go any further on successive electron affinities. This Born-Haber cycle is for the formation of copper oxide and lattice enthalpy of copper oxide. So the atom that eventually becomes a negatively charged ion, usually non-metals, that's going to be attracted strongly to an electron because it wants to gain an electron, just like any non-metal would want to gain an electron from GCSE. So there's strong attraction between the atom and the incoming electron, the first incoming electron. But this process creates a negatively charged ion, in this case the O- ion. So this will repel further electrons, in this case the E- that's there. So the second electron affinity now becomes endothermic, hence you've got the positive charge, the positive sign, excuse me. So it requires an intake of energy to happen. This is something well worth looking out for when you're drawing slightly more complicated Born-Haber cycles. They might throw this one at you and expect you to be able to understand and handle it. So looking at the same Born-Haber cycle, I'd like to draw your attention to the fact that in this case you had to do a first and second ionization. And this occurs with metals that have 2+ or 3+ ions. So you have to undergo the ionization energy twice. First ionization energy and second ionization energy. So we're also going to look at what happens if you have to do the electron affinity more than once, in the top right hand corner this time. So as you can probably guess, this would happen when you get more than one negative charge on the ion. There's another example here looking at sodium oxide. So if we look at the oxide ion as an example, you can see that the first stage is the receipt of an electron by an oxygen atom. That produces an O- ion. That's an exothermic change. But the O- and the second electron will repel each other, so that's a more difficult process, so therefore it's endothermic, it requires energy to happen. It's also worth mentioning, seeing as we're on this particular example, that because of the formula of sodium oxide, Na2O, you have to ionize 2 sodium gaseous atoms. So on the top left-hand corner of the Born-Haber cycle, you can see that there's actually 2 first ionization energies because 2 sodiums are being ionized from atoms to ions in gaseous state. So I've just circled and highlighted that along with the formula for sodium oxide, so you can see why you have to ionize sodium twice. Let's now have a look at what factors actually affect lattice enthalpy. So the 2 factors you need to look at are charge difference between the anions and cations. So the greater this charge difference, the greater the attraction. You also need to look at the size of the negative ion. As atoms gain electrons to become negative ions, the additional electron causes greater repulsion between the electron shells. So what this does is it makes the ion bigger than its atomic counterpart. If the atom had many shells to start with, the ionic radius will be large, and thus the nuclear attraction will be shielded. So the attraction for the positive ions in the solid lattice will be weaker. So a weaker attraction will mean a more endothermic lattice enthalpy. A stronger attraction will mean a more exothermic lattice enthalpy. So there's actually a close relationship between lattice enthalpy and the dissolving of a solid lattice into aqueous solution. So the first thing that has to happen is the lattice enthalpy has to be overcome. Once the lattice enthalpy has been overcome, what has to happen is all of the individual ions that have now been released from their electrostatic attractions to each other must be surrounded by water molecules. This second process is called the enthalpy change of hydration, or just hydration. Obviously the enthalpy change that accompanies it is called the enthalpy change of hydration. It'll be written as that in that way. Your delta sign, HYD, capital H, and then the standard symbol next to it. So if we draw out a K plus ion and a Cl minus ion, let me quickly show you what hydration actually is. So I've shown you how a water molecule could attract to the surface of a charged ion. Obviously a water molecule itself possesses partial charges, which I've included, delta plus and delta minus. You remember this obviously from your first year of chemistry. So what happens in the case of a positive ion is the delta minus oxygen attracts to the surface of the ion. Now this doesn't just happen once, this happens lots of times, as you can now see. So what happens is a hydration shell is formed. This prevents the ions from re-attracting to each other. And because the formation of attractions, just like the formation of bonds, is an exothermic process, hydration is always an exothermic process. So in the Born-Haber cycle on the left of the screen, you can see the relationship between lattice enthalpy, the enthalpy change of solution, which is the enthalpy change accompanying the dissolving of the ions, and the hydration. So there's obviously a delicate balance between lattice enthalpy and hydration enthalpy, which eventually determines whether the enthalpy of solution is exothermic or endothermic. So just to summarize these processes, the enthalpy change of solution is the enthalpy change that happens when 1 mole of a solute is dissolved in a solvent. If that solvent happens to be water, all the ions must be surrounded by water molecules. So there's an equation at the bottom left-hand side of the screen which tells you how to calculate the enthalpy of solution. You take the lattice enthalpy, and to that lattice enthalpy you add the total of all of the hydration enthalpies of the individual ions, which I've labelled up for you just above the relevant section of the equation. So if you were going to work this out using the Born-Haber cycle, you'd start where you have the solid lattice, and you'd work your way round as indicated using the indirect route, where you can see the dissolved ions. So the enthalpy change of solution is difficult, or if not impossible, to measure directly. So we use the lattice enthalpy data and hydration enthalpy data to work it out indirectly. Again, what we're doing is using Hess's law. So you may well have noticed on this particular Born-Haber cycle, we don't have the lattice enthalpy given. So this would be an example that they might give you in an exam to get you to work out the lattice enthalpy using the equation at the bottom of the screen. So let's have a go at that. So I've inserted the values in. The one value we don't have is lattice enthalpy. So we have to rearrange the expression so that lattice enthalpy is the subject. So we take the total of our hydration enthalpies and we subtract the enthalpy change of solution from that. So then we can state that the lattice enthalpy for potassium chloride, standard lattice enthalpy, is minus 711 kilojoules per mole to the minus 1. So much like lattice enthalpy, hydration enthalpy is affected by ionic charge and obviously ionic radius. So the greater the ionic charge, the greater the attraction. The lesser the ionic charge, the lesser the attraction. This has a bearing on the sign of the hydration enthalpy, whether it becomes more positive or more negative. And you have a similar relationship governing the ionic radius's effect on the enthalpy of hydration. So it might be worth pausing and just making sure you're happy with this, maybe pop it down on a flashcard before we go any further. So let's now have a look at a typical exam question on Born-Haber cycles. I've reduced the page size down a little bit so you can see the data and the Born-Haber cycle, plus which we have some room at the side to do our calculations. So the first thing we have to do is to fill in the values for each of the changes. So we have to work out from the change from each level to the next what's actually taking place. So what I've added is an overall sort of model that the Born-Haber cycle is based on, showing all the processes and in which order they come. Now what we need to do is to choose the correct enthalpy change values from the table and put them into the Born-Haber cycle. What might be a good idea is to pause the video, copy out the template and see if you can have a go at it yourself, and then play the video again when you think you've got an answer. So now I've put the numbers in. Have a look at the ones I'm about to highlight. And the reason behind that is that there's 2 sodiums in sodium oxide. So I have to multiply the atomization and the first ionization energy twice. So the way I'm going to do this is I'm going to use Hess's law, because that's what seems to be in many of the textbooks. I'm going to stick to that technique when I'm modelling how to do this in an exam. So the first thing I've done is I've written out all the processes that have to happen. So I start with my formation, and that equals all of those other processes as listed. I've listed them in order as I've climbed my way up and around the Born-Haber cycle. So the route I've taken is all the way around here, incorporating everything as I go. And if I add in all the data that I know, I can now lay this out as a calculation at the bottom of the page, like so. So now I rearrange so that the lattice enthalpy is the subject. And that gives me minus 2521 kilojoules per mole to the minus 1 as my answer. I've just highlighted that on the screen there in case it's a bit crowded at the bottom. So that's my answer I'm going to go with. So going on to the next part of the question, bring the page down a little bit so you can see that it was a 10-mark question in total. This is 4 marks here. It's asking you to think about which one of the following compounds has the most exothermic lattice enthalpy. So the thing to think about is ionic charge and ionic size, and you can also use your periodic table, because your periodic table will show you what is placed beneath what. As you go down groups, the size of the ion will increase. So I've jotted down a few notes to try and help you think about this and visualize it. So looking at the two positively charged ions, Ca2 plus and K plus, they have similar size because they're in the same period, same row of the periodic table, but they have different charge. With bromide and chloride, it's different, it's the other way around. It's a similar charge, with the same charge, but different size. So the logic behind the answer is laid out as the most exothermic lattice enthalpy being due to large charge difference causing greater attraction, and smaller sized ions meaning stronger attraction. So these two factors have to be combined. So the most exothermic lattice enthalpy belongs to calcium chloride. Now we've got to try and link that fact, that choice, to the logic we've used. So next to where it says large charge difference, I've in brackets put Ca2 plus and Cl minus to illustrate what I'm saying. And next to where I stated that smaller sized ions meant stronger attraction, I've just backed that up by saying that chloride is smaller than bromide. So let's now have a look at the mark scheme to both of these parts of the question to see how we did. So looking at our answer for our Born-Haber cycle, we doubled the atomization of sodium, we doubled the ionization of sodium, we put in the correct changes elsewhere, and we also got minus 2521, so we're fine on that count. So moving on to the second question, we correctly said calcium chloride, we correctly compared the sizes of bromide and chloride, we made reference to calcium 2 plus having a larger higher charge than K plus. And in the context of that, we correctly implied the strongest attraction between ions, because we said stronger attraction and greater attraction on two separate occasions within the answer. So that gets us our 10 marks. So at this point, if you've got any queries, do jot them down, maybe bring them into your teacher and have a chat to them about it, or come and see one of us in a subject extension. But for the time being, thank you very much for your time, appreciate your patience, and see you soon.